All right, kiddos, good class today. Thanks for your focus and hard work. So the question that we left off with is, why E, right? So we kind of talked about what E is by definition. We looked at the number that this expression, 1 plus 1 over x, all the x, is approaching as x is getting bigger and bigger. And it looks like it's starting to head towards 2.718 as x is getting bigger and bigger, right? So E is about 2.718, okay? It's an irrational number. It's about 2.718. So what's the big deal? Why E? Well, the first place in which we see E quite a bit is with continuous growth or decay models, right? And what it means to continuously grow or decay exponentially is not monthly, not daily, not even every hour, but at every moment. At every moment, something is either decaying, shrinking, or growing, increasing exponentially. Okay? Wouldn't it be great if we had continuous growth for our investments? Right? So not yearly, not interest compounded monthly, but at every moment. Okay? And when we do have an instance where things are growing or decaying exponentially and continuously at every single moment, that's where E, about 2.718, Euler's constant, pops up. You guys are probably familiar with this Pert model, right? So P is kind of like our initial value, whatever, right? It's kind of like the principal we started with when we invested with compound interest. It's a kind of a similar thing, right? T is the time, R is the rate, and A is the after, right? So it's the value after. Okay, so it's very similar to the model we already looked at, principal times 1 plus r over n all to the nt. It's very similar, but what we have now is we have continuous growth. Instead of n times per year, we have at every moment something is either growing or decaying exponentially. Okay, and if that is the case, we use this continuous growth model or decay model. Okay. So let's look at a real-life example of this, and this is actually useful in your lives, or other people's lives, perhaps. And it's called carbon dating, right? And carbon dating, here's the deal, right? Carbon-14 has a half-life of, I believe it's about 5,700 years, right? And with that, and knowing just that, we can measure, given the amount of carbon-14 left, and how that is measured, I know not. That's a good question for our science folks. But we can know how old bones are that are unearthed, maybe a dinosaur bone, or some sort of fossil, right? Just by measuring the amount of carbon that's left. So here's how we do it. Number one, we assume that carbon-14 decays exponentially, right? That's an important assumption, right? So we're going to use this model of not only exponential decay, right, because the amount of carbon over time decreases, but we're going to assume that it decays at every moment, okay? The way things decay in our natural world, it's not like once a month things decay and then they maintain the same, and then the first of the next month it decays a little bit more and then remains the same, right? So decay happens at every moment, okay, if it's continuous decay, which we assume, right? So I'm going to use this fact that when T is 5,700 years, what's left will be half of what we start with, right? And so essentially I'm going to use that knowledge, half of what I start with. So if I start with P, right, of carbon, and I end up with half of P, that's what half-life is, right? How much is left after, in this case, 5,700 R. So R is T is 5,700, and if we put in P, we end up with half of P, because that's what a half-life is. How much time does it take for half of something to decay? Okay, so now I can solve for R, right? I want to solve for R, the rate of decay, and in order to do so, I'm going to essentially divide both sides by P, boom, boom, getting rid of that, which essentially means that it doesn't matter what you start with, because I end up with half of whatever I started with, so it's almost irrelevant. Okay. Now I'm just going to solve this, right? In order to solve for R in the exponent, I'm going to log both sides, right? And to log both sides, I'm not going to take the common log because I have base E. I'm going to take the natural log, right? So I natural log both sides, And just as with the case with any logarithm, the exponent comes down. So on the left I have natural log 1/2, and on the right the exponent, 5,700r, times the natural log of e. But wait a minute, the natural log of e is just 1, since e, the base, to the first equals e, right? So the reason I took the natural log of both sides instead of the common log is because I just end up with, on the right, 5,700r, because the natural log of e is 1. Okay. Now I proceed to solve as usual, and I get, when I divide by 5,700, I get my r, right? And I'm going to turn to my calculator to see what on earth that is. And that's called the rate of decay, and some constant of decay. And I don't remember what it is, so I'm going to take the natural log of 1/2. And I'm going to divide that by 5,700. Okay? So what I now know is r is, let's see, this number, negative 1.216 times 10 to the negative fourth. So I'm going to move the decimal over 4 spots. Right? So it's going to move 1, 2, that's 1 0, 3, another 0, 4. Right? So this is my value of r, my rate of decay for carbon-14. Right? So to put it back into the context of this problem, the overall model we can use for carbon dating ends up being the amount with P initial present decaying continuously, such that in this case we found R to be negative 0.00011216 T years. So this is the model we can use for carbon-14 dating. Right. So the question again here is Pert. A, the amount after T years, is equal to P, the principal, the initial value, times E, Euler's constant, to the, and here's our R that we solved for, right? We had, knowing the half-life, 5,700 years, we're able to solve for R, which is the rate of decay, in this case continuous and exponential. Okay? So the question is, well, how do we use this, right? So if that's the formula we can use, what if a third of carbon-14 is left in, let's say, some bones, some old bones? How old are the bones? Right? So in order to solve this, okay, a third is left, so that means I want to get back for A 1/3 of what I started with. So if I start with P, I want to get back a third of P. Right? That would be a third left. And then E to the negative 0.00011216 T. Right? I want to solve for T. How many years? I want to solve for T. Right? How old? Okay? Well, you might say there's one too many variables, but E, remember, is not a variable. It's a constant. It's about 2.718. Right? And then what happens to the P's when I divide both sides by P? That's right. They go away. 0.001216 T. And now I'm right back to an exponential equation with the variable and the exponent, and we use logarithms to solve, right? And we can either rewrite as its equivalent logarithmic, or I think it's just as easy to do as we have and take the natural log of both sides, right? So if I natural log the left, I get natural log of 1/3. And if I natural log the right, that comes down 0.001216 T. And then I have times what's left, the natural log of E, right? But remember, the natural log of E is just 1, because E, the base of the natural log, to the first equals 1, right? So it's just times 1. And then to solve for T, I just divide both sides by that number, negative 0.00021216. And then I turn to my calculator to tell me what that number is, right? So I have, I want the natural log of 1/3, which I guess you could express as natural log of 1, which is 0, minus the natural log of 3 using the quotient property. I want to divide that by negative 0.00021216. Okay. And so this fossil is 9,034 years old. About, approximately. Okay. If it has a third of carbon-14 left in it, then based on what we know about the half-life of carbon and under the assumption that carbon-14 decays continuously and exponentially, we're able to tell that this particular fossil is 9,034 about years old. Okay? So that's one place in which we use E, Euler's constant. Exponential growth, which is continuous at every moment, or exponential decay, which requires something to decay, like carbon-14, at every moment continuously. Okay? Thanks for listening. See you in class tomorrow.